So I've had a look at how you need to increase the sampling frequency so it's high enough to capture the frequencies you want to look at and come across the concept of a Nyquist frequency. I want to examine the behavior of the Nyquist frequency and sampling a little further and deal with a phenomenon known as aliasing. So what I've got on the left-hand side here is some data, and the blue points are the sampling points, so the vertical lines denote where the blue points are going to be. The blue curve is the real data, so that's the actual physical phenomenon that we're sampling, and then you can see the orange line connects the dots, and that's just to guide the eye so you can see what's going on with the data that we're sampling. And this is just a cosine wave, and so when you look over on the right hand side here and the Fourier space, I'm plotting between the negative Nyquist frequency and positive Nyquist frequency, and we have two spikes, a cosine wave Fourier transforms to a pair of spikes, delta spikes, placed symmetrically about the origin, and so that's what's going on there. So now as I increase the frequency of my signal, but my sampling is not changing, I get closer and closer to the Nyquist frequency until the frequency of my signal equals the Nyquist frequency, and then you can see we're neatly sampling the peaks and troughs of our signal. And if you look closely on the right hand side here, as I increase the frequency a little more, the red delta spike is going to flip around to negative Nyquist frequency, and the blue is going to flip around to the other side. So we go higher and higher and higher, and then red and blue switch places and move back towards zero frequency, and we get back to zero when the frequency of my signal is equal to my sampling frequency, and that's when I no longer see any modulation or any frequency at all. I go back to zero because I'm just sampling the same point on the curve each time. And if I increase the frequency of my signal further, I keep going round and round through this sort of cycle. So it's got a little bit confusing as to what's going on here with the red and the blue spikes changing places. A better way to think about this is actually on a circle. So when you're taking a numerical Fourier transform, really the data in the Fourier domain lives on a circle. So as I increase the frequency of my signal, then my Fourier components start moving around my Fourier axis, and my Fourier axis is actually circular. So when I get to half the Nyquist frequency, I'm halfway around to the other side of the circle, and as I get to the Nyquist frequency, my positive and negative frequencies coincide at the positive negative Nyquist frequency point, and then they keep traveling around the circle in the same direction, but on a linear axis that looked like some kind of reflection or sort of jumping from one side to the other. But in fact, these spikes are just going round and round a circle like this. So maybe you can imagine that this Nyquist frequency can make things kind of complicated. If you have frequencies that are higher than Nyquist frequency, they will appear in your Fourier transform at frequencies below the Nyquist frequency, and if you have lots of frequencies everywhere, this can get messy very quickly. So let's just have a look at an example with 3 frequencies instead of too many. So the previous cosine wave examples had a single frequency. Now we're going to look at something that might more represent something you might do in a lab. So we've got some signal here that has 3 different frequencies, and each of these frequencies have different amplitudes. And then I'm going to plot the absolute square of the Fourier component. So I'm taking the Fourier transform and taking the absolute square and just plotting the positive frequencies. So from 0 up to 5 Hertz. 5 Hertz is my Nyquist frequency because in this example I'm sampling at 10 Hertz. So as long as my frequencies are less than my Nyquist frequency, the actual frequency I'm injecting into my system here is well represented by my Fourier transforms. Everything works out just fine. But as soon as one of my frequencies gets to the Nyquist frequency, then if you think about this thing on the circle, that would be reaching the maximum frequency and continuing around on my circle, and then the absolute value of that measured frequency starts to decrease and head back towards 0, and so you can see that that green frequency there has reflected off the end and is heading back towards 0. And now if you say, well, the actual frequencies here are 2.4 Hertz, which is fine, 4.7 Hertz, which is fine, and 7 Hertz, which is now being represented by this frequency here, which is clearly wrong. And so as your frequencies get higher and higher, your spectrum becomes increasingly incorrect. and you can see the frequencies bouncing off each end of these axes here, which, remember, on a circle they're all going the same direction, but here we've sort of cut that circle and we're looking at it bouncing backwards and forwards. Bummer. So as the frequencies increase, they don't just go away, they don't just walk off the end of the axis and you don't see them anymore. They actually get in the way by reflecting back off the Nyquist frequency or back off the zero and staying within your plot, but just appearing at the wrong frequency. So to fix this, you either need a low-pass filter so that no frequencies above the Nyquist frequency enter your system, that way they can't be reflected back and get in the way, or you need to increase your sampling frequency. Now, the way I presented this aliasing seems a little abstract perhaps, but it's actually something you're almost certainly familiar with, assuming you've watched TV or movies. Because when you capture a movie, you're doing it at some frame rate. You're taking some vision of the universe and splitting it up into frames, typically somewhere around 30 or sometimes 60 frames per second. And because you're sampling things, sometimes you get beating and aliasing. So here's an example with a bike tire that I filmed at 60 frames per second, and there's some tread pattern here, and you ask the question, how fast are the knobs moving past this pointer that I've inserted here? The maximum speed you can see them moving past would be at the Nyquist frequency if you're sampling, and sometimes they appear to be stationary, not moving past the point at all. Sometimes they're moving to the left, sometimes they're moving to the right. You don't actually find out which direction the wheel is moving until right at the end of this video, where the wheel slows down enough that you're no longer aliasing the vision that you're capturing at this 60 frame per second rate.